At the dawn of the jet age, the world was shrinking, but not fast enough. In the late 1950s and early 1960s, commercial aviation had already transformed global mobility, yet intercontinental travel remained an endurance test measured in long hours, fatigue, and the tyranny of time zones. Crossing the Atlantic still consumed most of a day. For governments, airlines, and industries that increasingly operated on a global scale, speed itself had become the final frontier. The problem was not merely how to fly higher or farther, but how to cut time in half without sacrificing safety, reliability, or prestige. In this environment, two former imperial powers, Britain and France, faced a strategic crossroads. Their aviation industries were rich in expertise, but threatened by the growing dominance of the United States. The solution they envisioned was not incremental improvement, but a leap so radical it would redefine what commercial flight meant. Out of this ambition emerged Concorde, a machine conceived not simply as an airplane, but as a statement that engineering could still unite continents faster than politics, markets, or geography ever could. The necessity was both practical and symbolic. Post-war Europe needed a technological flagship that could compete with American manufacturers and restore confidence in its aerospace sector. The idea of sustained supersonic transport promised a new era in which business leaders could leave London in the morning and arrive in New York before the local clock reached lunchtime. Engineers, policymakers, and economists aligned around a singular vision: time itself could be engineered. This was not a private corporate gamble, but a state-level commitment. Britain and France entered into an unprecedented bilateral treaty, binding their governments to share costs, risks, and technological secrets. The teams that formed under this agreement represented some of the finest aerospace minds of the era, drawing on experience from military aviation, early jetliners, and experimental research aircraft. Their challenge was immense. No commercial airplane had ever flown faster than sound for sustained periods, let alone done so while carrying passengers in comfort across oceans. The central obstacle was that supersonic flight rewrites the rules of aerodynamics. At speeds above Mach 1, shockwaves dominate airflow, dramatically increasing drag and heat. Traditional wing designs become inefficient, and structural loads intensify. Concorde's engineers responded with a solution that looked radical even by experimental standards: a slender delta wing, optimized not for low-speed efficiency, but for stability and lift at twice the speed of sound. This wing was not merely a shape, but a system, carefully tuned to manage shockwaves and distribute lift evenly across the airframe. The fuselage itself was engineered to withstand skin temperatures exceeding 120 degrees Celsius, generated by air friction during cruise. Aluminum alloys were pushed to their thermal limits, expanding several inches in flight, a phenomenon engineers had to anticipate down to the millimeter. Propulsion presented an equally formidable challenge. The aircraft required engines capable of delivering both high thrust for supersonic cruise and precise control during takeoff and landing. The result was the Olympus 593, developed through a complex partnership involving Rolls-Royce and Snecma. These engines were closer in philosophy to military power plants than to conventional airliner engines, incorporating afterburners or reheat to push the aircraft through the sound barrier. Integrating such systems into a civilian aircraft demanded unprecedented reliability and redundancy. A failure at Mach 2 over the Atlantic was not an option. Beyond engineering, the program carried enormous financial and political risk. Development costs soared far beyond initial projections, and the global market for supersonic travel began to shrink as environmental concerns and economic realities emerged. Sonic booms restricted overland supersonic flight, limiting routes primarily to transoceanic corridors. Fuel consumption was high, and operating economics were unforgiving. Yet Britain and France pressed forward, driven by a belief that technological leadership justified the expense. Concorde was never intended to be mass market. It was designed as a premium instrument, serving governments, executives, and travelers for whom time was the ultimate currency. When Concorde finally took to the skies, its first flight marked more than a technical milestone. It signaled a paradigm shift in human mobility. The aircraft could cruise at over 1,350 miles per hour, reducing the Atlantic crossing to roughly 3.5 hours. Inside the cabin, passengers experienced an environment unlike any other, a narrow but refined space, where speed was visible on cockpit instruments and subtly felt in the gentle climb to stratospheric altitudes. At 60,000 feet, the curvature of the Earth became perceptible, and the sky darkened toward indigo. Concorde did not merely transport people. It altered their perception of distance and scale. Airlines such as British Airways and Air France became the custodians of this new era. For them, Concorde was less about profit margins and more about brand identity. Operating the aircraft conferred prestige, signaling technological sophistication and global reach. Concorde became a fixture of high diplomacy, celebrity travel, and international business. Heads of state used it to cross oceans in a single morning. Financial markets adapted to the idea that executives could attend meetings on both sides of the Atlantic in one day. Time zones, once rigid barriers, became negotiable. Yet the very attributes that made Concorde extraordinary also limited its longevity. The aircraft's operating costs remained high, and the fleet was small, constraining economies of scale. Environmental awareness grew, and public tolerance for noise and emissions diminished. The tragic accident in 2000 cast a long shadow, prompting exhaustive technical reviews and modifications that further increased costs. Although Concorde returned to service, the broader context had changed. Airline economics after the turn of the century favored efficiency and volume over speed and exclusivity. Supersonic travel, once heralded as the inevitable future, became an anomaly. Despite its retirement, Concorde's legacy endures in profound ways. Its design philosophy influenced subsequent high-speed research and informed computational fluid dynamics methods now standard in aerospace engineering. Materials science advanced through lessons learned about thermal expansion and fatigue at extreme speeds. Operationally, Concorde proved that international collaboration on a grand scale was possible, laying groundwork for future programs such as those led by Airbus. Culturally, it remains an icon, instantly recognizable and deeply symbolic of an era when ambition outweighed caution. Concorde's story is ultimately not one of failure or excess, but of audacity. It demonstrated that engineering can compress the world, not by erasing distance, but by mastering it. The aircraft did not disappear because it was flawed, but because the world recalibrated its priorities. Efficiency replaced speed, scale replaced spectacle. Yet the question Concorde posed remains unanswered. What is humanity willing to build when limits are treated as challenges rather than constraints? In its final analysis, Concorde stands as a triumph of engineering and imagination. It united continents through velocity, bridged nations through collaboration, and left behind a blueprint for what is possible when ambition is matched by skill. The lesson it offers is enduring and clear. Progress in aviation, as in all human endeavors, is written by those willing to challenge the boundaries of physics, economics, and expectation. The history of aviation is written with steel, ingenuity, and the will to defy limits. The aircraft that emerged from this vision was not merely fast. It was an engineering ecosystem in which every component existed because no conventional alternative would survive the environment it was about to enter. At sustained supersonic speed, air behaves less like a fluid and more like a compressible barrier. Shock waves form at the nose, wing leading edges, and engine intakes, and managing them became one of the defining challenges of the entire program. The solution was a variable geometry intake system, a masterpiece of analog control engineering. These intakes slowed incoming air from supersonic to subsonic speeds before it reached the engine compressors, preventing destructive pressure surges. At cruise, more than half of the aircraft's total thrust was generated not by the engines themselves, but by the careful recovery of pressure inside these intakes. In effect, the airframe and propulsion system functioned as a single integrated machine. Thermal stress shaped every design decision. At Mach 2, friction with the atmosphere heated the airframe to temperatures far beyond those experienced by subsonic jets. Engineers accepted that the structure would expand in flight, growing several inches longer at cruise altitude. Rather than fight this reality, they designed for it. Expansion joints, flexible fuel lines, and sliding fittings allowed the aircraft to breathe with temperature changes. Even the fuel system became a thermal management tool. Fuel was pumped around the aircraft to absorb heat, shifting the center of gravity during different phases of flight and stabilizing the aircraft without traditional trim surfaces. This was not improvisation. It was precision engineering built on deep theoretical understanding. The wing, often described as elegant, was in truth brutally functional. Its delta shape minimized wave drag at supersonic speeds while remaining controllable at low speeds through the use of vortex lift. At takeoff and landing, the aircraft adopted a high angle of attack, lifting its nose dramatically to generate sufficient lift. This posture defined the silhouette of the aircraft on the runway and necessitated one of its most distinctive features, the droop nose. The hinged nose cone lowered during takeoff and landing to give pilots adequate visibility, then raised in flight to restore aerodynamic efficiency. Every visible peculiarity of the aircraft existed because physics demanded it. The risk profile of the program extended far beyond engineering. Financial exposure grew as development timelines stretched and projected markets contracted. Early forecasts imagined hundreds of supersonic transports crisscrossing the globe, but regulatory barriers and public opposition to sonic booms quickly reduced viable routes. Political commitment, however, locked the program into continuation. Britain and France had bound themselves not only legally but symbolically. Canceling the project would have signaled technological retreat. Pressing on became as much a matter of national identity as of transportation policy. When the aircraft entered commercial service, it did so into a world that was both awed and divided. For passengers, the experience was transformative. Acceleration through the sound barrier was subtle yet unmistakable, marked by the steady climb of the Mach meter and the quiet competence of the flight deck. Time itself felt negotiable. Breakfast in London and lunch in New York became routine. Jet lag, once an unavoidable tax on intercontinental travel, lost much of its power. For a narrow but influential segment of society, the globe felt smaller and more accessible than ever before. Airlines adapted their operations around this new reality. Crew training emphasized systems knowledge at a depth uncommon in civil aviation, reflecting the aircraft's complexity and performance envelope. Maintenance programs were meticulous, driven by the understanding that supersonic flight tolerated no shortcuts. Concorde operations became showcases of discipline, where engineering precision extended into every procedural detail. The aircraft demanded excellence, and in return delivered reliability that consistently defied skepticism. Beyond aviation, the socioeconomic impact rippled outward. Financial markets adjusted to faster information flow and face-to-face negotiations conducted across oceans in a single day. Diplomacy accelerated. Media coverage turned each departure and arrival into an event. Concorde was never invisible. Its presence on an airport ramp or streaking across the sky symbolized progress in motion. It became a cultural artifact, appearing in films, art, and literature as shorthand for speed, luxury, and modernity. Yet the same factors that elevated Concorde also isolated it. Fuel efficiency lagged far behind emerging wide-body aircraft optimized for mass travel. Environmental scrutiny intensified, focusing on noise, emissions, and the broader sustainability of supersonic flight. The economics of aviation shifted toward scale and accessibility rather than exclusivity. Airlines faced increasing pressure to justify investments in aircraft that served prestige more than profitability. The accident at the turn of the millennium marked a decisive inflection point. While investigations identified specific technical causes and corrective measures were implemented, the broader impact was psychological as much as operational. Public perception shifted, and confidence, once taken for granted, required rebuilding. The aircraft returned to service with improvements that enhanced safety but added weight and complexity. By then, the external environment had changed irrevocably. The post-Cold War world prioritized efficiency, cost control, and environmental accountability. The decision to retire Concorde was not the result of a single failure, but of cumulative realities. Maintenance costs rose as the fleet aged. Replacement parts became increasingly specialized. Passenger demand, while loyal, could not offset the economic pressures facing airlines in a competitive, margin-sensitive industry. Supersonic travel, once framed as the future, was reclassified as a remarkable but singular achievement. Even in retirement, the aircraft continued to teach. Engineers studied its data to refine computational models of high-speed aerodynamics. Materials scientists drew lessons from decades of thermal cycling at extreme conditions. Modern aerospace programs, from advanced military aircraft to experimental civil concepts, trace intellectual lineage back to the challenges Concorde solved. It proved that sustained supersonic transport was not a theoretical aspiration, but an operational reality. Concorde's deeper legacy lies in its demonstration of what coordinated ambition can achieve. It was built not by a single corporation chasing profit, but by nations committing to a shared technological vision. It showed that political borders could be bridged by engineering collaboration, producing a machine that served as both tool and symbol. In an industry often constrained by incrementalism, Concorde stood apart as a leap. The world that retired Concorde is not the world that built it. Yet the questions it raised are returning. Advances in materials, digital flight controls, and environmental mitigation are reopening conversations about high-speed civil transport. New generations of engineers look back not with nostalgia, but with analytical curiosity. They see an aircraft that pushed boundaries honestly, revealing both the promise and the price of speed. In this light, Concorde is best understood not as an endpoint, but as a reference point. It marks the outer edge of what 20th century engineering could accomplish when ambition was given priority over caution. Its retirement closed a chapter, but it did not erase the lesson. Aviation advances when humanity chooses to confront limits directly, accepting risk in pursuit of transformation. Concorde embodied that choice, and in doing so, permanently altered the trajectory of flight. With the aircraft fully integrated into commercial service, the true measure of its achievement became visible not in specifications, but in daily operation. Each flight represented a controlled negotiation with physics. Takeoff was a carefully choreographed sequence, engines advancing into reheat as the aircraft accelerated down the runway, lifting off at speeds that exceeded the cruising velocity of many subsonic jets. Climb profiles were steep and deliberate, designed to minimize noise exposure near airports before the aircraft pushed out over open water. Only then did the transition begin. The throttles advanced again, the aircraft pierced the sound barrier, and the outside world slipped into a different regime of flight where distance collapsed and time bit. At cruise, Concorde operated in an environment few humans had ever experienced. Flying above most weather systems, turbulence was rare, and the aircraft rode a narrow corridor of stability near the edge of the stratosphere. The sky darkened noticeably, and the sun's position became a more prominent reference than the horizon. Passengers were not merely traveling. They were participating in a technological event. The Mach meter in the cabin was not decoration. It was a reminder that the aircraft was sustaining a speed once reserved for experimental and military platforms. This was commercial aviation at its most audacious. The economic model supporting these flights was unconventional by design. Ticket prices reflected not just transportation, but access to time itself. Concorde passengers paid a premium to reclaim hours, sometimes entire days, from their schedules. For global finance, law, and diplomacy, this advantage was tangible. Executives could attend morning meetings in Europe and evening engagements in North America without surrendering productivity to jet lag. Governments leveraged this capability for rapid response and symbolic presence. The aircraft became an extension of geopolitical influence, shrinking response times and amplifying visibility on the world stage. Operational discipline was relentless. Concorde demanded precision from everyone involved, from flight crews to ground engineers. Checklists were exhaustive, and deviations were not tolerated. The aircraft's systems were deeply interconnected, meaning that small anomalies required careful interpretation rather than reflexive action. Pilots trained extensively in systems management, understanding not only what each component did, but why it behaved as it did at different speeds and temperatures. This depth of knowledge set a benchmark for professionalism that influenced training philosophies across the industry. As years passed, the aircraft accumulated a record that contradicted early skepticism. Dispatch reliability was high, and mechanical failures were rare given the stresses involved. Concorde demonstrated that supersonic transport, when engineered and operated rigorously, could achieve levels of safety comparable to subsonic fleets. This operational success reinforced the notion that the barriers to faster travel were not purely technical, but increasingly economic and regulatory. At the same time, the external environment continued to evolve. The oil crises of the 1970s reshaped attitudes toward fuel consumption and efficiency. Wide-body aircraft entered service, offering unprecedented capacity and lowering per seat costs. Air travel democratized rapidly, shifting public expectations away from speed and toward affordability. Concorde existed outside this trend, serving a niche that valued time above all else. Its role became that of a flagship rather than a workhorse, a visible reminder of what aviation could achieve at its outer limits. Culturally, the aircraft's influence deepened. Concorde transcended its function to become an icon of modernity. Its silhouette symbolized optimism in technology, a belief that engineering could overcome constraints imposed by nature. Museums, designers, and filmmakers embraced it as shorthand for progress. For an entire generation, Concorde represented a future that felt tangible and immediate, even as broader aviation trends moved in a different direction. The turn of the century introduced a harsher reality. The accident in 2000 shattered the aura of invincibility that had surrounded the aircraft. Investigations were exhaustive and uncompromising, examining every layer of design, operation, and infrastructure. The findings led to tangible modifications that enhanced safety, including reinforced fuel tanks and revised operating procedures. From an engineering standpoint, the response demonstrated the system's resilience. Problems were identified, understood, and corrected. From a commercial standpoint, however, the damage extended beyond technical resolution. Public confidence is a fragile currency in aviation, and Concorde relied heavily on perception as well as performance. The grounding that followed disrupted operations and accelerated financial pressures already mounting on airlines. When flights resumed, they did so into an industry transformed by global uncertainty and shifting priorities. Security costs increased. Passenger demand softened. Airlines reassessed every asset through the lens of sustainability and return on investment. In that environment, Concorde's margins narrowed to the point of inevitability. The decision to retire the fleet was therefore strategic rather than reactive. It acknowledged that the aircraft belonged to a specific historical moment, one defined by state-backed ambition and tolerance for high costs in pursuit of prestige. By the early 2000s, aviation had become a ruthlessly optimized industry, driven by efficiency metrics and competitive pricing. Supersonic speed, once the defining metric of progress, no longer aligned with prevailing economic logic. The final flights carried a weight that extended beyond aviation enthusiasts. They marked the end of an era in which speed itself was celebrated as a public good. Crowds gathered to watch departures and arrivals, aware that they were witnessing history in motion for the last time. Pilots and engineers who had dedicated careers to the aircraft understood that its retirement was not a judgment on their work, but a reflection of changing values. Concorde had fulfilled its mission. It had proven what was possible. In the years since, its influence has only grown clearer. The data collected over decades of supersonic operation continues to inform research into high-speed aerodynamics, materials, and propulsion. Lessons learned about thermal management, structural fatigue, and systems integration remain relevant to contemporary design challenges. Modern computational tools owe much to validation against real-world performance data generated by the aircraft. Equally important is the philosophical legacy. Concorde challenged the assumption that progress must always be incremental. It embodied a willingness to accept complexity and risk in exchange for transformative capability. This mindset contrasts sharply with later trends toward conservative optimization. Yet as new generations confront global connectivity, environmental constraints, and technological limits, the balance between ambition and restraint is again under debate. Today, renewed interest in supersonic and even hypersonic transport reflects a cyclical return to questions Concorde first forced into the open. Can speed be reconciled with sustainability? Can advanced materials and digital control systems mitigate the costs that once made supersonic flight untenable? These questions are being explored with tools unavailable to Concorde's designers. But the foundational challenge remains the same: engineering time. In retrospect, Concorde's retirement was not an ending, but a pause. It closed one chapter of aviation history while leaving behind a reference against which all future high-speed ambitions are measured. The aircraft demonstrated that the world could be united not only by networks and agreements, but by velocity. It showed that when engineering, politics, and vision align, the result can redefine human experience on a global scale. The Concorde story, viewed through this lens, is less about what was lost and more about what was revealed. It exposed both the power and the cost of pushing beyond conventional limits. It forced aviation to confront the reality that technological triumph does not guarantee permanence. And it left an enduring challenge to future innovators. If speed once united the world, can it do so again under new constraints? This question ensures that Concorde remains relevant, not as nostalgia, but as a benchmark. It stands as evidence that humanity has already crossed the sound barrier together, carrying passengers, ideas, and ambition at twice the speed of sound. Whether that achievement will be repeated or surpassed is a matter for the future. That it was accomplished at all is a testament to the extraordinary reach of human engineering. As Concorde receded from daily operation into memory, its influence migrated from the runway to the drawing board. Engineers, historians, and policymakers began reassessing the aircraft not as a commercial product, but as a technological catalyst whose effects extended far beyond its limited fleet size. Its legacy unfolded quietly, embedded in methodologies, standards, and design philosophies that reshaped how aerospace problems were approached. Concorde forced the industry to confront regimes of speed, temperature, and integration that conventional airliners never encountered, and the solutions developed for it became reference material for decades to come. One of the most enduring influences lay in aerodynamics. Concorde operated in a narrow envelope where small changes in shape or angle produced disproportionate effects. To manage this, engineers refined analytical techniques that later evolved into advanced computational fluid dynamics. These tools, validated against Concorde's extensive real-world data, became indispensable in modern aircraft design. Supersonic military jets, experimental research aircraft, and even high-performance subsonic airliners benefited from insights gained through Concorde's Delta Wing, vortex lift behavior, and shockwave management. The aircraft effectively bridged the gap between wind tunnel theory and operational reality. Materials science absorbed similar lessons. Concorde's sustained exposure to thermal cycling pushed aluminum alloys to their practical limits. Engineers learned how repeated expansion and contraction affected fatigue life, seal integrity, and structural tolerances. These findings informed maintenance philosophies and design margins across the industry. Later programs adopted more conservative assumptions about thermal stress, while also accelerating the search for advanced composites and heat-resistant alloys. In this way, Concorde indirectly contributed to the material revolutions that define modern aerospace engineering. Systems integration may be its most understated contribution. Concorde was among the earliest commercial aircraft to treat fuel not just as energy, but as a dynamic control medium. By redistributing fuel to manage center of gravity, engineers reduced drag and stabilized the aircraft without relying on traditional aerodynamic trimming. This holistic view of aircraft systems anticipated later fly-by-wire philosophies, where computers manage complex trade-offs between performance, efficiency, and stability. While Concorde itself relied on analog systems, the conceptual framework it established proved timeless. The influence extended into organizational and political domains. Concorde demonstrated that multinational cooperation on a technologically demanding program was possible, even under intense economic and political pressure. This experience shaped future European aerospace collaborations, most notably the emergence of Airbus as a global competitor. The confidence gained from Concorde's successes and the lessons learned from its limitations informed how large-scale projects were structured, funded, and governed. In this sense, Concorde helped redefine not just how aircraft were built, but how aerospace institutions functioned. Culturally, the aircraft achieved a status few machines ever reach. It became a symbol of an era defined by optimism and technological progress. Concorde appeared in advertising, cinema, and popular media as shorthand for speed, sophistication, and ambition. Its image conveyed more than transportation. It represented mastery over time and distance. Even those who never flew on it recognized its significance. The aircraft entered public consciousness as an artifact of collective aspiration, embodying the belief that humanity could engineer its way past natural limits. As museums began preserving retired airframes, Concorde transitioned from tool to teacher. Static displays revealed the complexity hidden beneath its smooth exterior. Visitors encountered the dense network of systems, the tight tolerances, and the compromises required to sustain supersonic flight. For students and young engineers, Concorde became a case study in ambition tempered by reality. It showed that groundbreaking innovation demands not only creativity, but also discipline, patience, and acceptance of trade-offs. Meanwhile, the broader aviation ecosystem continued to evolve. Environmental priorities gained prominence, and efficiency became the dominant metric of success. Supersonic transport, once celebrated, was re-examined through the lens of sustainability. Concorde's fuel consumption and noise footprint stood in stark contrast to emerging expectations. Yet this reassessment did not diminish its value. Instead, it reframed Concorde as a boundary marker, defining what 20th century technology could achieve and where its limitations lay. The conversation around high-speed civil flight did not end with Concorde's retirement. Rather, it entered a dormant phase. Advances in digital modeling, materials engineering, and propulsion technology gradually reopened questions once thought settled. New concepts emerged, promising reduced sonic booms, improved efficiency, and lower environmental impact. These proposals, while technologically distinct, consistently traced their lineage back to Concorde. The aircraft served as both inspiration and cautionary tale, reminding designers that speed must be balanced against economics, regulation, and public acceptance. In strategic terms, Concorde influenced how governments and industries think about flagship projects. It demonstrated that not all value is captured in profit and loss statements. Prestige, knowledge transfer, and technological momentum carry weight, even when commercial returns fall short. This perspective continues to shape decisions around space exploration, advanced defense systems, and experimental aviation programs. Concorde legitimized the idea that some endeavors are justified by what they enable rather than what they earn. Over time, the aircraft's narrative matured. Early debates framed it as either triumph or folly, success or failure. With distance, a more nuanced understanding emerged. Concorde was both extraordinarily successful in achieving its technical goals and inherently constrained by the context in which it operated. It solved the problem it set out to solve: sustained, safe, commercial supersonic transport. That the world later chose a different set of priorities does not negate that achievement. The aircraft's legacy is therefore evolutionary rather than linear. It did not spawn a direct successor, but it reshaped the intellectual terrain of aviation. Its influence is visible in design processes, regulatory frameworks, and cultural attitudes toward innovation. Concorde expanded the industry's sense of the possible, even as it clarified the costs associated with pushing beyond established boundaries. In this way, Concorde occupies a unique position in aviation history. It is not merely a retired airplane or a nostalgic symbol. It is a reference standard against which ambition is measured. Whenever engineers propose to fly faster, higher, or more efficiently, they inevitably confront the questions Concorde already answered and those it left open. The aircraft's true contribution lies in this enduring dialogue between aspiration and reality. By redefining expectations and exposing limits, Concorde advanced aviation as much through its constraints as through its capabilities. It proved that human ingenuity could conquer the sound barrier in routine, commercial service. It also revealed that progress is shaped as much by societal choice as by engineering skill. That dual lesson ensures that Concorde's influence continues, long after its final landing, embedded in the evolving story of flight. In the final accounting, Concorde stands apart not because it was perfect, but because it dared to exist at all. It emerged from a moment in history when ambition outweighed caution and when nations were willing to stake prestige, resources, and intellectual capital on a single idea. That time itself could be engineered. Concorde was the physical manifestation of that belief. It did not merely shorten journeys. It redefined the relationship between distance and human activity, compressing continents into hours and reshaping expectations of what aviation could deliver. The aircraft's withdrawal from service was often framed as an ending, yet it is more accurately understood as a transition. Concorde did not fail in its mission. It fulfilled it completely. It proved that sustained, routine, commercial supersonic flight was achievable, safe, and operationally viable. That achievement alone places it among the most consequential machines ever built. Its retirement reflected not a shortcoming in engineering, but a shift in global priorities. The world that once valued speed as the ultimate metric of progress began to prioritize efficiency, accessibility, and environmental responsibility. Aviation evolved accordingly. This evolution does not diminish Concorde's relevance. On the contrary, it sharpens it. Concorde serves as a benchmark against which future ambitions are measured. Any proposal to return to supersonic travel must contend with the realities Concorde exposed: the economic cost of speed, the environmental implications of noise and emissions, and the complexity inherent in operating at the edge of the atmosphere. Yet it also serves as proof that these challenges are not insurmountable. They have been confronted before, with tools far less advanced than those available today. The aircraft's deeper legacy lies in how it reframed engineering itself. Concorde demonstrated that innovation at the highest level demands integration across disciplines. Aerodynamics could not be separated from propulsion. Materials science could not be divorced from thermal physics. Operations could not be isolated from design. Every decision echoed through the entire system. This holistic approach has since become a defining principle of modern aerospace engineering. In this sense, Concorde was not only a product of its time, but a precursor to the systems thinking mindset that defines contemporary design. Equally enduring is the human dimension of its story. Concorde was built by individuals who accepted uncertainty as the price of progress. Engineers, pilots, technicians, and policymakers collaborated across national and cultural boundaries, united by a shared objective that transcended immediate returns. Their work stands as a reminder that the most transformative achievements often arise from collective vision rather than individual gain. Concorde was not owned by a single company or nation in spirit. It belonged to an idea that humanity could move faster together. The cultural resonance of the aircraft reinforces this lesson. Concorde became a symbol not because of marketing, but because of meaning. Its silhouette represented confidence in technology and optimism about the future. It suggested that engineering could elevate human experience, not incrementally, but dramatically. Even in retirement, the aircraft commands attention, drawing crowds and inspiring curiosity. It continues to provoke questions about what aviation should strive to be and how far society is willing to go to reach the next horizon. As aviation looks forward, the questions Concorde posed remain unresolved and therefore alive. Advances in materials, propulsion, and digital control systems reopen possibilities once constrained by 20th century limitations. Environmental considerations challenge designers to reconcile speed with sustainability. Economic realities demand new models that align innovation with broader access. In each of these debates, Concorde's experience serves as both guide and warning. It reminds us that progress is rarely linear and never free. Ultimately, Concorde's story is not about nostalgia. It is about perspective. It shows that technological milestones are shaped as much by human values as by technical capability. Concorde existed because a generation believed that speed was worth the cost. Its retirement reflected a recalibration of that belief, not a rejection of innovation itself. Future breakthroughs will emerge under different assumptions, guided by new priorities, but they will inevitably trace their lineage back to the moment humanity first crossed the sound barrier with passengers aboard. In closing, Concorde endures as a testament to what happens when ambition is matched by skill and resolve. It united the world not through networks or negotiations, but through velocity. It transformed the abstract concept of time into a variable that could be engineered, managed, and sold. And it left behind a lesson that transcends aviation, that the boundaries of progress are defined not only by physics, but by the courage to challenge them. The history of aviation is written with steel, ingenuity, and the will to defy limits.